Okay, I'll give a minute for people to settle down. Good morning. Hope you guys have a nice day two of the conference. Um, yeah, so my name is Nikhil Barthwal, and I'll be talking about evolutionary architecture, how to build systems that can evolve over time. Okay, and the way I've structured this talk is that I start with what is the problem, what is evolutionary architecture, why do we need it, and then I go about establishing a couple of principles. So, I mean, in some form or another, you probably are aware of these cohesion, loose coupling, connaissance is a very common term in software architectures. Then I go about certain architecture patterns and how you can make them evolutionary. So, architectural patterns for evolutionary architecture. And after that, I mean, we have talked about various building blocks. Then we talk about how these blocks would communicate with each other. So, communication patterns and how Conway's law can be applied. Then we talk about data, which in my opinion is somewhat more important than the software architecture, because when you look at data, data is what stays constant over a long period of time. Architecture, your code gets rewritten all the time. And towards the end, I have like bunch of best practices in various domains, how you can follow those good practices for evolutionary architecture. Okay, so let's start with defining the problem that we are here to solve. Okay, so a common conception of people is that, you know, we want to build a software, we have some end goal in mind and we define an architecture. Okay, this is like a, you know, foundation for the building that we want to build, and then we take this whole big project into small parts. You run them in sprints, adjusting as you go, the agile, or you could do it in waterfall, doesn't really matter. But the key thing is that architecture is thought as a foundation on which your entire system is going to be built. And once it's done, it's like a blueprint. But the problem is that you are making an implicit assumption here. You're making an implicit assumption that you know about the future, when unfortunately or fortunately, how you look at it, we actually don't. And the reason is requirements keep evolving all the time, and you really cannot predict how those requirements would evolve over a period of time. Also, you start with certain assumptions that this is how market is, this is what my customer wants, etc. And as you go over your journey, you go back and you realize that some of the assumptions that you have made are actually wrong and you need to adjust. But the problem is that your architecture, once you have defined, it's very hard to change. Because what happens is that once a base architecture is defined, it's very hard to change. And this leads to a phenomenon called software decay or software rot, right? Which is kind of a slow deterioration of your software over a period of time that eventually leads your software to become faulty. And the problem is the slow deterioration. Slow deterioration often is actually worse than fast deterioration, because when fast deterioration happens, you see something is not working, you fix it. Slow deterioration, you know, you get used to things like going bad over the period of time. Yeah, maybe there are some faults, we can fix them later on. Yeah, it kind of works, let's not do a rewrite, etc. So over a period of time, because your architecture was defined in the beginning and your requirements changed in a way that made that architecture redundant, you know, you lead to this software decay principle. So this is where evolutionary architecture comes in. So what is evolutionary architecture? This is the textbook definition of evolutionary architecture. And what it says is that it's basically an approach where you really don't have an end state, you kind of evolve. So I have this idea, you know, I do a little bit of a blueprint and then I evolve over a period of time. I make my architecture such that it's easy to change. In some sense, it's the whole agile principles applied to software architecture. Because the thing is, when we talk about agile programming, agile processes and everything, most of the time these agile processes talk about development. They actually don't talk about architecture. We define a problem and then we break down into problems and then break down into small parts, and then we have sprints how we continue. So our architecture is the one that stays constant. How we implement that architecture is usually done in an agile way. And what evolutionary architecture says is don't start with architecture as a constant and then use an agile method for development. Bring that agile methodology right at architecture level. Treat the architecture itself as something that evolves over a period of time. So essentially, Your architecture is designed in a way that you're optimizing your architecture so it's easy to change in future. That's what it is all about. And what that basically means is that you have certain dimensions, and we'll talk more about what dimensions are. For example, you have certain security, compliance, legal requirement. You define basically some characteristics. My software has to have these properties. These are like kind of invariant property. Obviously, I want my architecture, I want my system to be secure. I mean, that's a no-brainer. Now, what exactly is that security? What do we mean by secure? How we implement it? Those are details. But I want security because, hey, security is important for me. Similarly, I want like compliance. I don't want to break laws. I don't want to get fined. And then what you do is once you have these requirements or these characteristics, or whatever you like to call it, you have some way of evaluating how good your architecture is across the dimensions that you care about. So there you define what is a fitness function, right? In some sense, fitness function is something that we implicitly use in terms of performance, right? You might have an SLA, okay, I don't care what my architecture is, but what I want is that all my services should respond within 100 millisecond, right? So I have these performance characteristics that I want my SLA. Now, we are not talking about what architecture you're going to use. You're just talking about requirements at an architecture level. My architecture should be such that I should be able to serve all my customers within a certain my architecture should be such that I should have basically a way of following certain compliances, and my fitness function essentially defines how my architecture is across these characteristics. And fitness functions itself is a little bit finicky because what happens when you actually implement these fitness functions is that sometimes you have a conflicting requirement, right? You want your system to have very high throughput, but when you have very high throughput, your device utilization might go high. When you have like faster response times, right, your throughput would decrease. So sometimes it requires an adjustment. You know, engineering is all about making the compromises. So how do I know that, can I assign a score to my system design and say, well, this is something that I'm willing to, this is something that I'm willing to measure. So I take my response time, I take my performance, I take my security. Can I somehow come up with a number, or not even a strict number, but like a guideline of making a decision that, you know, I have these two alternatives, which one is better? So that's what fitness function is. It's essentially a guiding function. And once I have that, I start with an agile methodology. So I say, okay, fine, this is what my base architecture is. So this is like kind of a sprint one. I implement it, my requirements come, you know, there's an additional requirement. Okay, fine. So I need to make changes to my base architecture. I can make changes in these 4 areas. Which one is better? So I make the change to the architecture. I evaluate my fitness function for these 4 alternatives. And I say, well, based on what I have defined above, this architecture is better. So you basically start with a loop of starting your base architecture. As requirements evolve, your architecture evolves over a period of time, and your fitness function is basically the guide that will let you know which direction you're getting. So here are some examples of architecture definition. We have already talked about performance security, right? So you have auditability. I want to be able to audit my systems. You know, the governments love auditing, and I think European governments particularly love auditing. Performance, right? We want performance. Security, kind of obvious. Data, we have certain data compliances, certain way in data can be handled. Privacy, around data privacy is a big topic, GDPR, etc., etc. Legal and compliance aspect, we all want scalability. We want to be able to scale. Our business grows. Who doesn't want the business to grow? So architecture should be such. So these are the examples of various dimensions that I can define my fitness function. And like I said, fitness function can be a strict objective function, or fitness function can basically be a loose set of principles. It doesn't really matter how you define fitness function. The key criteria of fitness function is that you should be able to evaluate alternatives and choose which one of the alternative is better. As long as you can do that, your fitness function is actually good enough. So now we go into a classic agile loop, right? Agile build, measure, learn. What do? Once you have a base architecture, you make guided incremental changes. So that's the build part of it. And then you kind of measure. You put it in the feedback loop for everyone to learn. And how you measure is actually a little bit tricky, because architectures can be a little tricky to measure. Sometimes you can do some kind of static analysis or, ahead of implementation. Sometimes you actually can't, because a lot of time performance characteristics is something that you can't predict. So often the measurement is done on your build pipeline. So I have this architecture, I just run this loop, I put it on the build pipeline, I run a bunch of performance tests, a bunch of security tests, and I now see what my performance characteristics is going to be. So that's how I'm going to measure. So measure could be basically an analysis of the architecture before you implement. It could also be something that you evaluate at a later point of time. It doesn't really matter how you measure, but the key thing is, there's this one quote, that if you cannot express something in form of a number, then your engineering is something wrong. So you need to have a measure, because you need to know which direction you're heading. You need to know, are you going in the right direction? You need to know how progress you're making, etc., etc. So measurement is very important. So classical evolutionary architecture still follows the build, measure, learn that you have basically in implementation side of it, except that you're now dealing early on in the cycle. Now here, I'm actually going to introduce the principle of connaissance, which is kind of coupling also. You would have heard the term of loose coupling, tight coupling, and you would have probably heard loose coupling is good, but why? Why is it important? Why is it important for architecture? How does it impact the evolvability of architecture? To start with, we will start with a textbook definition of what coupling is, right? Two components are coupled or connaissant if what happens is that change in one requires a change in other one, right? So imagine I have a distributed system I have an API, I have a REST API, system A called system B. Turns out that system B has changed its format, right? It's changed its API definitions, changed its response time. System A, which is dependent on system B, has to make that changes. So we say these changes are coupled. Now, in general, in any sufficiently large system, you have these components that they will be coupled to each other definitely, because they are operating together. It's a question of how much are they coupled, right? So coupling is basically a measure that you can use to define how much one component is dependent on other component, and we'll look into certain architecture patterns of why coupling is bad, how we can reduce it at a later point. But essentially, there are two forms of coupling, right? There's a static level coupling. So static level coupling is something that you determine at compile time. For example, I'm using certain API, I'm using certain library, right? The library changes its class format, it adds, deletes methods, attributes, so on. I'm using that component. My code will not compile if that dependency is changed, right? So that's static level coupling, which is kind of a good level coupling because you can detect it at compile time. So that's static level coupling. There's a second one that is dynamic level coupling. I'm basically dependent on API responding to me within a certain second, especially if it's an asynchronous distributed system. I really cannot determine whether my system is coupled or not until I actually execute that couple. So that execute the system. So that's what dynamic coupling is. So these are two forms of coupling. And generally, you want to be more on the static side than on the dynamic side. So looking at, let's say, dynamic, typical examples would be execution timing, right? You want a certain value to be present. You want things to happen in a certain order. You want things to respond within a certain, that's all dynamic, right? That's not something that I can look at the source code. I can see these two codes are being coupled. And you want to move away from dynamic to static. The end goal is that you want to reduce the coupling as much as possible. You obviously cannot get rid of coupling altogether because your components operate with each other. But what you want to do is reduce the coupling and as much as possible move from dynamic to static. So static, where you're dependent on certain naming conventions, you're using certain algorithms, certain position in your API, ordering of your variables, etc., etc. That's all static coupling. Okay, so related principle is cohesion. Okay, and in some form of another, we always use cohesion. We just don't call it cohesion, but the textbook definition is that degree to which elements inside a module are together. So think of coupling and cohesion as two different things. Cohesion is inside. So you have a module, how does things inside the module interact? And coupling is how does that things inside the module interact with outside the module. So coupling and cohesion are actually kind of complementary to each other. Okay, so here's a definition that you have one component calling another component, and you have these different parts grouped together in a module. In fact, cohesion is one of the things that is the foundation of object-oriented programming. If you look at object-oriented programming, what is object-oriented programming? Object-oriented programming says that you can divide your system in these sort of objects and classes, and these classes have an external interface and they have an internal state, and all the related things are packed together in one class. So you will have like a customer class, you will have like a product class. So customer class might have an ID, customer class might have a name, address, gender, age, etc., etc. Attributes of a customer. So customer becomes one module, and all the things that belong to a customer are grouped together in a class. So object-oriented programming, in some sense, it doesn't really use the word cohesion, but essentially when you're doing object-oriented programming, you're implicitly following the principle of cohesion in the sense that you group everything related to one entity together in an object. That's cohesion for you. And what you observe is that high cohesion has low coupling. Why? Because when they are grouped together, most of the calls will happen with each other. That group will, as a whole, interact with another module. So that's the reason why coupling is going to be low. Whereas if you look at the diagram, if you've done a mistake in the way you have grouped items together, then it gets very confusing. The communication gets structured. So low cohesion means tight coupling. Coupling is bad because when you're looking at architecture, what you want to do is, you know, your architecture is going to change over time. So what you want to do is that I should be able to, you know, modify one part of it, and it should not break that I have to make a modification 100 places, right? So, you know, in good old softwares, I remember a quote that somebody said from Oracle, that if you, Oracle database, it's obviously an old C code, and if you add a feature, 5,000 tests would break. So people will then go and fix all these tests, because back in the day, software architecture as a discipline probably wasn't as advanced as it is today, right? The code was not properly modularized. So what you really want is, you want the module to act like having high cohesion. So if I change something inside the module, then I shouldn't be changing all the dependency. I might have to change some, but I want to minimize it as much as possible. That is the reason why I have as low coupling as possible. Again, I'll go back to my object-oriented programming. You decide to add a new attribute to the customer, right? So you have, let's say, gender, male and female, and then the law says that, you know, certain people are non-binary. So I don't want to have people categorized as male and female. I want people to be categorized as male, female, or non-binary. That's fine. That's an attribute of a customer. You can change that. But if I change an attribute of a customer, I don't want to change product definitions. There's no reason why customer attribute should affect the product. So this is the reason why what I want to do is, if I want to make a change at one place, I should be able to work through it without modifying the entire system, because if I do that, then my architecture is hard to change. The first thing we learn about evolutionary architecture is that things are going to change, and you want your architecture should be such that you have to optimize it for changing. And that is the reason why coupling is bad. And that is the reason why you want high cohesion in order to reduce coupling. So I'll introduce another topic of domain-driven design. Domain-driven design is basically a big topic. You know, you could have an entire conference on domain-driven design. I'll just barely scratch the surface. But essentially, domain-driven design is basically an approach where you have a model of the system, right? And essentially, you connect the implementation to this model that is evolving, right? You're designing a software for a car. You have these model of how the car operates. You basically, as this model operates, your implementation would change. It has certain building blocks. We'll talk about bounded context in a little bit more details, but there's bounded context, which is, you know, basically one model for a complex system is usually big. So what you basically do is, rather than having one models, you have like several submodels that talk to each other. And each submodel is called as a bounded context. And then you have entities. Entities are essentially immutable objects. And then you have value objects, right? So in classic programming, your objects, mostly when you talk about object-oriented programming, it's basically objects. And when you're talking about entities, they're the immutable components. Entities are the objects, and value objects are basically the immutable content. So like a record or something like that. And then you have aggregates, right? In domain-driven design, most of their code is actually going to be entities and value objects. And then you have aggregates, basically things you treat them as together. And then you have a service which defines a transaction. So these are the various building blocks of domain-driven design. If you want to learn more about domain-driven design, there are some classic textbooks. Now, I won't go too much into domain-driven design, except how domain-driven design is actually connected to evolutionary architecture. So I'm going to talk about bounded context here. So what is bounded context then? Essentially, you have a complex system. You can't have one model. So you define multiple submodels, right? Salespeople might have another one, support have another one. And these are these complex submodels that interact with each other. Now, how can we use domain-driven design, and especially bounded context, for evolutionary architecture? A domain model is a collection of bounded contexts. We talked about that. And what bounded context essentially gives you is a boundary for partitioning. Now, in previous slides, we talked about cohesion. We talked about, having your system into modularized code, etc., etc. But the real question is, how do I take this system and how do I follow the modules? I understand that I need to group items together, but is there a principle I can use? And that is where bounded context basically gives you. Bounded context, what you can do is gives you that partition that say, okay, these things belong to this group, these things belong to this group, and then you have a high cohesion inside each submodel, bounded context. And then if you have done your job very well of modeling your system, you have low cohesion between, say, sales and support. So bounded context basically is the guiding principle that will allow you to partition your system into small parts that allows you to follow the principle of high cohesion, which in terms leads to low coupling. And that's where DDD actually comes in, fits in evolutionary architecture. Another common architecture pattern is layered architecture, especially during services, right? So when you look at certain systems, I mean, Google is probably the most common one that follows layered architecture quite a lot, is that you define this complex system in form of layers, right? And each layer has an interface, and you have these various layers. So you have these database, you have this persistence layer, you have this business layer, presentation layer, essentially UI, you want to store the data, you want to process the data, you have characteristics of data, etc., etc. So you define this architecture into layers, and then each layers would be such that there are interfaces between these layers. And the key idea is that layer above or layer below, layer above can only interact with the layer below through the interface. So now what you can do is you can change things inside the layer but not change the interface. This eventually will lead you to something like microservices architecture, etc. But that's what the layered architecture is. Layered architecture is one form of practicing evolutionary architecture. That said, there are some downsides because there are certain issues that cuts across multiple layers. So layered architecture is one form of evolutionary architecture, right? But not the only one, because you have to look at your problem and decide that this one layered architecture works or not, and we'll talk about other forms also. But essentially, layered architecture is one good form of practicing evolutionary architecture. Now, what about other ones? Another ones, and now we are going into the classic microservices and monolith services, is a modular monolith. In some cases, monolith services are pretty good. Most of the startups would start with a monolith and maybe eventually go into the microservice architecture. And there are certain startups that started with microservice architecture and realized it's too complex and went back to monolith. Monolith by itself is not a problem. But what the monolith becomes a problem is that when you are having this big ball of mud, so you have a lot of this code that talks to each other in a hazarded way. So what modular monolith says is that you take your monolith services into different modules that talk with each other. They don't have to exist as separate services. They're all part of the same service, right? If they exist as separate services, it becomes a microservices. So think of it this way, that you divide your system into microservices, but you don't actually run them as an independent services. They still run together in form of the same code base. That's what modular monolith is. So it consists of dividing your logic into modules, and then each module is kind of independent and isolated with its own schema. It's talking to a database, everything, except that it's still part of the same service. The other part of it is microservices. So what I can do is, for a number of reasons, I don't want to use modular monolith. I don't want to use monolith, right? Because monoliths have drawbacks. If a monolith creates interdependencies between the team A owns module 1, team B owns module 2. Team A wants to make a change, it has to deploy the whole service, it affects module 2. Sometimes there are interconnected issues. So you want to use microservices. Microservices have their own advantages. Essentially, microservices is a system where you have services that are small, interconnected, and they work together. And it's just an approach of, rather than viewing your web service as one single one, you have a set of small services. With that communicates through a standard HTTP or whatever, or it could even be an asynchronous through a message bus. So microservices is nothing but an assembly of loosely coupled services. In fact, microservices, realize or not, is another architectural pattern that you're using for evolutionary architecture. And in microservices, you have these contracts. And the key idea is that contract basically is a format from one component to communicate to another component. The key idea is that if you have done a good job of isolating your services, then your contracts should not change often. So microservices can immediately evolve with if the contracts don't change, they can evolve independently. Now there are times when the contracts between the services change, so it requires a little bit of coordination, but the key idea is that does not happen often. The interesting thing about all these microservices and monoliths and all these things are, they are basically rehashing the same principles that we have been following ages, because microservices is object-oriented programming applied to distributed systems. I mean, if you look at what object-oriented programming is, what is object-oriented programming? Same thing. You have an interface, right, the public methods, and then you have the private attributes of a class, of an object, and you can't access the private attributes, so you have to go through the interface, and your system basically consists of these objects working together. So microservices is the same thing. You have all of these services connected to a database. You can't access the database directly. That's your private state of the service, and you have this public interface that talks, through which you can communicate. Interestingly enough, object-oriented programming itself came from microbiology, because one of the early object-oriented pioneers, Alan Kay, was a microbiologist. And when software was a new discipline, what he saw as software was like a human body. What is a human body? Human body consists of cells organized in tissues. And when you look at these cells have cell walls, and then there are nucleus, and you can't access anything of what is happening in nucleus. You have to interact through cell walls. So he says, well, I can view software like a human body. So I have these objects which have internal state and public interface, and they work together. They are grouped in form of modules. So that's the tissues, and these modules work together to build a system. So that's how microbiology, and then you have object-oriented programming, and then you have microservices all evolving. Pretty much the principles stay the same. You have like isolation, you have a cohesion, you have a coupling, you have loose coupling. Microservices contracts can sometimes be strict in the sense that service A connects with service B. I have a fixed JSON schema. RPC is actually pretty strict, right? I have to have formats of how communications would happen. You can use protobufs and Avro. I define my protocol, and then I have the stubs that generate, compress, and decompress. The problem with the strict is that if you want to modify, let's say I want to have a system, I want to add an attribute, it's going to be very difficult because it requires an entire, like you have to define a new protocol, and you have to recompile your code. You will basically have, the changes have to be done on both sides, right? You don't want the high coupling. So the key idea of evolutionary architecture is that you should move from strict to loose. That's your direction. Loose means I can have schema-less XML, right? So for example, my services evolve. My services can send more information. It can add more key value pairs to an existing JSON. The reader doesn't really have to know that. Reader can ignore that, right? So reader, let's say I'm sending 10 pieces of information, the reader only cares about 5, so it parses the 5 and ignores the remaining 5. So that what it does is it lets me evolve these systems independently without coupling. Key value pair is another example. I can have the same thing. Instead of having binary protobuf Avro, I can have some kind of compressed JSON or an XML. So applying the principles of evolutionary architecture means that trying to change the schema or the contract between the service from strict to loose. Now we talk about communication patterns. So we have talked about components. We have talked about how components are operating, how they are packed into modules. We have talked about, cohesion, everything, but these components talk to each other, communicate. So now we want to talk about communication patterns. When you look at your system, you can basically divide patterns into 3 parts. So tier 1, tier 2, tier 3. Tier 1 is what impacts your customers directly. Tier 2 is something that interacts with customers indirectly, and tier 3 has little to no impact. Now I'll go with examples. You're designing something like Amazon, right? Your order management service is a customer facing. Your service goes down, you can't place an order. Shipping service is something that tier 2. Your shipping service goes down, your system still works, your shipment will be delayed. It's not blocking the system, it's just affecting it. Tier 3 is something like monitoring. Customer doesn't care if your monitoring system goes down. Typically, the tier 1s are implemented because of synchronous, and we'll explain why it's typically request response synchronous. And it's a good idea to implement tier 2 and tier 3 in an event-driven asynchronous from an evolutionary point of view, and we'll see why shortly. So let's look at request response pattern. Here I have a pattern that connects, right? This is all synchronous. The key advantage is that it's a very easy to implement, that's great, but the biggest advantage is it has a better error control. Now, if one of the service fails and you have like a 400 error or something like that, immediately you would notify. Tier 1 services tend to be something that should have very high availability, so you want better error control. But the drawback of tier 1 is that it increases the coupling, right? Now every service has to know about how other services talk about, it has to deal with all these issues, that if you want to add a new service, right, that talks to 3 other services, you not only have to add that service, you have to modify 3 other ones also. So it's difficult to scale, it increases the coupling, but it's required for better error control. So the way systems are designed is that you try to move all the services into tier 2 and 3 as much as possible, and only keep the bare minimum on tier 1, the ones you actually need that are very critical, because not every service is very critical. You're using Netflix, your recommendation service goes down. You can still watch a movie. Your system is not out of control. The only thing is that if you log in, you will not see recommendations of other movies. That's fine. But if you have a particular movie in mind, you can still watch it. You can search for the name and watch it. Then you have the second one, event-driven. Okay, event-driven uses a message broker. Now, which is an asynchronous form. The advantage is that it's much more scalable. It increases decoupling. I can add and subtract new services to the message broker. I don't have to modify any one of them, right? So from an evolutionary point of view, event-driven services are much easy to evolve because they're inherently decoupled. The only problem is that there is no traceability, right? Product service sends a message asynchronously. What if the shipping service is down? Product service doesn't really know. You don't know what happened to that message when it went, because there is no synchronization, right? It's asynchronous. So that is the reason why you don't want to use event-driven services often in your tier 1 service. So typically when you go to something like order, you place an order, what happens? Well, order management service will take your order and will give you an ID. Your order number ABC has been placed, here is your ID, and then sends a message on the message broker to a tier 2 service, which will then process it asynchronously, and that's much more scalable. So now we're going to introduce some architecture patterns like event sourcing. In some form of another, event sourcing is we have been using it for many years. We just don't call it event sourcing, but essentially event sourcing is a pattern where you model your system as state of events, right? And then you can store all these events, and then that can trigger a state change, and then you can replay or the system to build your state or roll back in particular point of time. What are the examples of? So the advantage of event sourcing is that because you have all of these events, you can create future workflows that you have not thought. So from an evolutionary architecture point of view, event sourcing is quite important. Examples, very common examples of event sourcing is bank ledger, right? When you look at bank ledger, what is a bank ledger? Bank ledger, I open up an account, I have an account with $0. I put in money, I withdraw money. Every transaction is an event. Bank stores all these transactions. And what is my sum total? What is the state of my account, the amount of money? It's basically a sum total of every transaction. If I withdraw, it's a negative. If I deposit, it's a positive. Add all these numbers, and that's what my state of the system is. Git is another event sourcing system. So we realize that event sourcing is something that we have been using for ages. We just don't call it event sourcing, right? State is your source control. Source control, you're changing all these deltas, and basically the current state is a sum of every commit that you have made. I can replay that commit, I can go back. Now, why can I create a future workflow? Because in Git, you might realize that the commit you did 10 days ago was wrong, so you can go back, cherry pick, remove that commit, and then put back all those commits. You can do that. You can do the same thing with bank, right? I'm looking at my credit card statement, and I realized a month back, this transaction is a fraudulent transaction. I call up the bank rolls back in time, removes the transaction, then rolls forward and puts all those transactions together. So these systems that are event source are basically, you can create future workflows, so they are easy to modify later on. You can also create multiple views, so adding applications that can process the same event but create a different view. Facebook, for example, I post an event on my timeline. Oh, I got married. My personal section updates, my photo section ignores, my timeline updates. I paste a photo, my personal section ignores, my photo section adds that, and my timeline adds that. So the same event can be processed in multiple views when you have these event source systems. Another one is command query responsibility segregation, often called CQRS. It's actually a must for event sourcing, and what it does is all your requests can be categorized into forms. It's a read or a write. Right? Write is a command, it modifies something. Read is basically query. When you have event source systems, it's very hard for you to query that state because the state doesn't really exist, in the sense that you have to replay that state to build one. So what you basically do is, as states come, you basically create a query model, which can be the complete state or a subset, and then you can query. Inherently, this system becomes eventually consistent. Eventually consistent system is a one that will achieve consistency over a period of time, but not immediately, because if there's a new command, the system will go in the database, the state will be updated, so you don't really have it immediately on the read model. CQRS pattern is essentially a must for event sourcing. We are going to go into sagas. What is sagas? When you have all of these distributed systems, the components interacting with each other. I'm actually going a little fast because I am lacking time, sorry. You have these long running transactions. Every transactions, what you do is you have a rollback transactions to handle a failure. So you can have all of these modules, and then you can have their actions, and then you can have compensating actions. So here is an example. I make a transaction, I create the transaction, I was supposed to go to 3.3, this failed, so I start with rollback. Example, I want to transfer $100 from my account to your account. So I initiate the transfer, bank takes 100 account out of my account, so that's the first step. Then it's about to deposit $100 to your account. What happens? You close your account. So what happens to that $100? That bank will roll back the transaction, in the sense deposit that money back in my account. So that's an example of rollback transaction. We talk about data. Unfortunately, or fortunately, but data is actually more important. So when we want to change schemas, we should rigorously test, right? We should version, because schemas change can be very hard to track. We duplicate data for decoupling, but although it can create problems of consistency, in the sense I want to query, it's not scalable to have everything in one database. So I can have like two different databases, basically have different views of the same data, as long as there are no consistency issues. And stored procedures we absolutely want to avoid, because they are very hard to test and refactor. And we have to ensure, once we have duplicated the data, or even otherwise, that there has to be consistency or referential integrity. One thing that I want to take away is, data schemas outlive your application. Data will stay constant for a very long time. Your application will change all the time. So, I should probably rearrange my talk and talk about data first and architecture second, because in many ways, data is more important than architecture. Okay. So we talk about schema isolations. The whole point of microservices is independent isolability. We talked about, strict schemas and loose schemas. So once we have these loosely coupled services, right, it reduces the team interdependency. So teams can evolve faster with each other. So that's the advantage microservices would give you. But the key thing about microservice is that you should not share the database, right? So database schema is all isolated, because if the same service accesses the same database, if you change the schema, you will actually have to change multiple services, and that kind of breaks your coupling. So you want greater evolvability, which is the whole purpose of architecture, evolutionary architecture. We talk about Conway's laws. Organizations, that's a textbook definition, but essentially a common example is that if you are building a compiler and you have 4 teams, then you'll have a 4-pass compiler, right? Your software will mimic the communication structures in your organization. So team A, team B, that's how your service is going to be. How can you use it in practice? Structure the teams to look like target architecture. So it's easy for you to achieve that architecture. We'll go into some of the best practices. I'm actually going to split them in 4 sections. So you have like feature selection. Because requirements will change, take reversible decisions as much as possible. You want to be obsessed about solution, not a problem. A common startup mistake. People care about, a lot about problem solution. Prefer evolvable over predictable. You can't predict. So basically, make things that are evolvable. Don't do excessive customizations, because customizations can actually harm you more than they can do good. Build a culture of experimentation. You don't know everything you need to know. Actually, I think the second point is obsess over problem, not solution. I think the words got interchanged, sorry. But anyway, culture of experimentation. Have the culture where you can experiment, because you don't know everything. So experiments will give you what you need to know about the unknowns. Design decisions. Don't architect for the sake of architecting. Prototype as your way to know unknowns. Certain things you don't know that they are going to be a problem. So there are problems and you know the solutions. There are problems you don't know the solutions, and then there are certain problems that you don't even know they exist. The unknown unknowns. So prototyping will let you discover those unknowns. Defer decisions for as much as you can, because you want evolvability, but at a certain point of time you can't defer it anymore. Avoid leaky abstractions. Like leaky abstractions happen when your edges and jars are somehow dependent on the abstraction details of adjoining layers, which you don't really want. You want those layers to talk through the interface, right? So understand if there are any leaky abstractions, fix them. Make things immutable as much as possible, because state is the root of all problems. I mean, that's where the functional programming is basically based on, right? Make the variables immutable and functions to manipulate them. So immutability will constrain and will not give you unnecessary side effects. So we're talking about some technology choices in terms for evolutionary architecture. Prefer libraries over frameworks, because frameworks constrain your thinking, whereas libraries will basically give you a free run on how you can evolve your system. Update frameworks aggressively, because frameworks are much more constraining, but libraries can be passive, assuming libraries are backward compatible. You should always be careful with low code, no code tools, because low code tool implicitly makes a lot of assumptions about your system. When you start with low code, what happens is that 80% of your code is very easy to do with these low codes. But the last remaining 20%, you're going to have hell lot of problems, because low code or often no code tools are often not customizable. So you want to be careful using them. Have multiple governance model. You can't have one model like for open source, one model for closed everything. You have to have multiple governance model. One size fits all rarely works. Third-party dependencies are often to be used with care, because dependencies will give you dependency tree, right? A dependency A belongs to dependency B, so you're going to pull this library, it will pull 10 other libraries, and then you'll have version conflicts, and that will constrain you. Very often than not, what you really need when you pull a library, you might need 1 or 2 functions, especially if the library is like open source. I find it much easier that if I just need 2 functions from a library, I'll just cut and paste that function and paste it in my code, as opposed to bringing that entire library. We'll talk a little bit about evolvability, right? Versioning is really a good thing. Prefer internal versioning, not just to your services, to your data as much as possible. Do not support more than 2 versions at a time, because then you get into a lot of complexities if you're supporting a lot of versions. You architect your system for testability. So your system should be such that I should be able to test my architecture, right? After all, I want to evaluate my architecture using fitness function. Use anti-corruption layers, so layers in between when you talk to external parties, right? Sometimes you have issues like you have missing data, etc. So you need some mechanism to compensate all that. Be conservative in sending, but liberal in receiving. The same is essentially the loose contract, strict contract. Don't send information that you don't need, but the receiver is very liberal. So if receiver sees that there is more information than what I need, it can ignore the information that it doesn't need. So it's liberal in receiving, but strict in sending. Every time you break a contract, use versioning. Pretty simple. And that's about it. I'm up for questions.